Hey everybody, welcome to this video on thermal imaging. I'm going to try to give you an overview of how thermal imaging works and some of the key concepts behind it. So what is thermal imaging? We're essentially going to measure the temperature of an object via remote sensing. That could be a sensor on a satellite, an airplane, or a thermal camera that you're holding in your hand, or any kind of thermal camera. And the basis of this is we're going to take pictures in a wavelength that our eye cannot see. Our eyes are evolved to see in the visible wavelengths, 350 to 740 nanometer. Thermal remote sensing takes place in the far infrared. That's way out here, from 2.5 up to 20 microns, typically often in this long wave infrared zone right here. So why do we use far infrared wavelength? So the key is that we're usually trying to measure the temperature, at least in earth science, of objects that are relatively cool. Quite often that would be the earth or the human body, things that are much cooler than, say, a star, like the sun. And so if you look at the black body spectrum, you can see that cool objects like Earth actually have an emission spectra that's peaked in the far infrared, right about 10 microns. Whereas the sun is peaked in the visible, which is great when we want to see during the day, but it's not good for measuring the temperature of objects. And if we were to measure thermal radiation at a shorter wavelength in here, essentially everything we see would be swamped by what's coming from the sun. So by measuring at longer wavelengths, like say 10 microns, we actually get out to a point where the sun's radiation is not impinging on us, and we can get a cleaner measurement of radiation that's coming only from the Earth's surface or from a human body, something like that. So why would we even want to measure temperature? Well, in Earth science, it's very important because temperature can discriminate based on the body properties of a material. What's going on inside of the material, rather than what's happening just on the surface. So for example, when we take a picture in visible wavelengths of light, that light is reflected off only the outer couple microns of the material. So for example, if a rock is covered with dust or is covered with soil, a picture in visible wavelengths wouldn't tell us anything about what type of rock is underneath there. But temperature actually radiates from much deeper within the surface. So perhaps looking at how temperature changes over time might reveal what's beneath that surface layer. More importantly, temperature is often actually the thing we're trying to measure. There's countless earth science applications where temperature is critical. Temperature of the oceans, lakes, atmospheres, temperature of soil and crops and permafrost, and the temperature of distant planets or stars if you're an astronomer. So temperature itself is pretty important. So a quick example of a satellite that does this, the Advanced Very High Resolution Radiometer. It collected a few bands in the visible and near infrared, and then collected these two bands, 4 and 5, out in that key far infrared zone. And this was an incredibly important mission for actually mapping ocean temperature. It was able to create global maps of ocean temperature fairly frequently. And for example, it was able to help us discover and document El Nino, right? Where we have, during La Nina, warm pools in the western Pacific, and then during El Nino, we have that warm surface water coming up to the coast of South America. It would be very hard to visualize this with only ocean temperature buoys. So satellite remote sensing is essential here. Okay, so what's the theory behind this? The theory really starts with this idea of the black body. And so a black body is an idealized thermal emitter. It's something that emits photons in a predictable pattern. And the key thing about a black body is that hotter objects emit more photons at shorter wavelengths. And we just talked about this with the sun. So the hotter an object gets, 3,000, 4,000, 5,000, 6,000 Kelvin, the more photons it gets, right? So you get more photons at this peak, but also notice the peak shifts towards the visible spectrum, okay? So essentially what we have here is the pattern of photon emission is changing in a predictable way based on temperature. And we're going to be able to exploit that to then measure those photons and convert to temperature. I'm actually going to skip what a black body is, but go ahead and look up a black body on the internet. I usually think of a black body as being a black stove that's in thermal equilibrium and is emitting this predictable radiation. So very importantly for us, the black body spectra is described by Planck's equation here. So in this case, radiance is equal to all this stuff, including Planck's constant h, the speed of light c, divided by wavelength. That's critical. Got wavelength in there a couple times, and then temperature is down here as well. So if we know this, if we know radiance because we've measured it on a thermal camera or a satellite, we can then turn around and solve for temperature. And we're going to know all of the other things. And essentially what we're doing is we're measuring the radiance, one of these lines, and we're going to convert it to temperature. So it's very important to recognize that remote sensing measures what's called the radiant temperature. That's essentially how hot we think it is, right? And it's inferred from how much radiation is coming out of that object. And that's different than the kinetic temperature. The kinetic temperature is the actual object. If you went and stuck a thermometer inside the rock, you'd measure its kinetic temperature. The radiant temperature is its kind of apparent temperature based on how much it's radiating. These two things are related by this term called the emissivity. It's another fractional term, and what it is, it's the emitted radiance divided by what the emitted radiance of a perfect black body would have been, okay? So suppose you've got a rock, it's at 40 degrees Fahrenheit. The emissivity is whatever radiance, the ratio of the radiance it's actually emitting divided by the radiance that would have been emitted by a black body at 40 degrees Fahrenheit or Celsius. I forget what I said. You get the idea. So emissivity is a fraction, ranges between 0 and 1. And for a black body, by definition, the emissivity is always 1, right? And here's that described mathematically. That'll come back in the next video. So you may want to write that down. So of course, in practice, most things are not black bodies. It really is a theoretical construct. So we have these two other categories that most materials fall into. That is a gray body, which exhibits the same pattern as a black body, scaled down by an emissivity factor. Let me show you what I mean. Here's wavelength, here's radiance. We just saw that a black body curve looks something like this dashed line. A gray body at the same temperature would emit something along this lower dashed line. Has the same shape, but it's scaled down by a factor. That's a gray body. A selective radiator is the opposite. It follows its own pattern. It might kind of mimic the black body, but then you might have these big gaps where it's not emitting much radiation. And that's because most materials and most rocks, for sure, are selective radiators. They're not able to radiate certain wavelengths of energy typically because their molecules cannot vibrate with that particular type of frequency. So they're unable to actually radiate in that wavelength. And that would be a selective radiator. So the world's greatest example of a gray body is water. Water's a perfect gray body. It essentially has an emissivity of 0.95 at all wavelengths. So that means whatever wavelength you choose, water's emitting roughly 95% of the radiation that it would be if it was a black body. right? So it perfectly mimics the black body curve here. And that's a huge deal. That means that because we always know the emissivity of water, that means we can reliably determine temperature from satellite imagery. We just measure the radiance from a satellite, and we use Planck's equation to estimate the radiant temperature, and then we know that radiant temperature is essentially 95% of what the true kinetic temperature would be. So this is an example from Lake Tahoe where water temperature was measured using the thermal band from the MODIS satellite sensor. Now I will say before you get too excited, unfortunately most Earth surface materials, even plants, concrete, soil, rock, are selective emitters. So you don't necessarily know what their emissivity is a priori. It makes it a lot more difficult to estimate temperature. Not to say it can't be done, it is done, but you have to be a lot more careful. So stay tuned for the next video where we're going to actually work through how you compute temperature from radiance. Thanks for listening.